The high Arctic is generally conceded to be the toughest environment in the world. It's barren, windswept, vast, adjectives that evoke human response. From an engineering point of view, perhaps the key adjective is cold. This frigid terrain is the location of Polaris, a huge new mine being opened by Cominco. It's the northernmost metal mine in the world, situated at 76 degrees north latitude in the high Arctic archipelago on the southwest shore of Little Cornwallis Island, about 80 miles from the magnetic pole and 60 miles from Resolute Bay, the main transportation hub of the high Arctic. This plan shows the development area. Bechtel Canada was project manager. A basin had been dug to receive a concentrator assembled in the south and floated north on a barge. A dike pushed the shoreline out to deep water. Big ore vessels need a deep-sea dock, a difficult engineering job in the Polar Sea. Tower Arctic Limited was given the go-ahead to build the dock consisting of 4 sheet pile cells, each 85 feet in diameter, joined by smaller cells. Major equipment and basic material was brought in by sea the year before, but additional bulldozers, trucks, and personnel vehicles were flown in from our permanent yard at Resolute. By early March, we were set up on the sea ice with maintenance sheds, workshops, and a warm-up trailer for the crew. Most of what we needed was in place. Unusual crew members were a team of purebred huskies brought along to provide a constant polar bear watch. We brought in divers to carry out underwater work and monitoring. The first undertaking was to make a final survey of bottom conditions in the dock area. Whenever a diver is down, the Jolly Roger flies over the hole. The underwater survey of the selected dock site showed foundation conditions that made the dock stability critical. The diver took down a rope to stake out the outline of each cell on the ocean floor. Soil samples were brought up for analysis, and after a final examination of the sea bottom, a new satisfactory site was located. The bedrock here is broken limestone overlain by 10 feet of silt. The water is 50 feet deep and the ice is 40 inches thick. The silt will retain the sheet piles during construction. Instead of customary marine equipment, we decided to utilize the Arctic cold and build a 9-foot thick ice platform from which to work. The ice platform will be in a C shape and will be anchored to the shore at each end of the dock area. Loose snow, cleared to prevent slush forming, was used to make a dike to contain the water during flooding. We began flooding on March 1st. The drilled hole acted as its own ice pipe, and pulling the auger out served to prime the pump. We used 3 pumps of a helix type that won't freeze. We found that with frequent thin applications of water, as long as the temperature didn't go above minus 25 degrees Celsius, we could build from 1.5 to 3 inches of ice a day. Gauge stakes were set in the ice to monitor thickness and rate of build. As the platform thickened, the dikes were raised. Auger and pump motors suffered frequent failures of their plastic components due to the Arctic cold, and a steady supply of spare parts was needed. Calculations indicated that a 9-foot thick platform would be safe for a long-term load of 100 tons. But for a day or two, it could support as much as 300 tons without serious ice creep or flooding. The night worked. In 2 months, there'd be 24 hours of daylight, and the ice would begin to soften. Each section was flooded every 7 hours, day and night, with a new hole drilled in a different place each time to prevent mounding. A problem had been found in the area of the dock itself. A large block of multi-year ice, frozen into the first-year ice, with its top jutting 3 or 4 feet above the surface. We needed help from the night diving crew to assess its size and to see whether it was bottom-bound. The diving hole could freeze over in as short a time as a dinner break. A lamp attached to a very long cable was let down. The diver always stayed in the heated tent till the last moment so that his respirator wouldn't freeze up. The lamp cable was paid out while the diver literally outlined with light the edges of the submerged block. At the same time, men on the surface traced in dye the path of the light shining up through the ice. We found that the block would have to be removed because it would interfere with the construction of 2 of the main cells. It was 17 feet thick. To get rid of it required imagination and improvisation. The method decided on was to cut off the projecting top and hollow out the ice block by drilling and blasting, making a huge sort of dugout canoe, which would then float to the top where it could be removed. A trencher with blades adapted for cutting ice went into action. This ice mass could be an Ice Age relic, a fragment from the north of Ellesmere Island that's drifted down through the straits over the centuries. Blasting had to be handled carefully because ice behaves differently from ordinary, and not even the experts have had much experience with blasting it. A specialist from the explosive company came up to advise and observe. A hole or crack in the dugout wall would flood the excavation and end the process. As the work proceeded, it became more hazardous. If there had been a breakthrough, a man would have lasted only a very short time in the -2 degrees Celsius water. The divers frequently checked the progress from below by looking up to see how much light came through. Work on the ice platform had progressed far enough for the blasted material to be carried off the platform, but the banks had to be kept low so that they wouldn't trap drifting snow. The divers had found a friend. He'd follow them underwater, cashing in on the oxygen in the trails they left behind. Never having seen men before, he enjoyed their company, and it was mutual. The building of ice continued. The platform was reinforced by steel cables frozen into it. Augers were lengthened several times by welding 2-foot extension pieces onto the end. The finished platform was over 700 feet long and spread 200 feet to seaward. Where it joined the shore, a natural hinge mechanism had developed. A few small cracks caused by tidal action were of no consequence. Construction of the dock itself began with marking the exact position of each cell. The divers brought their tent as near as possible to the work area. The trencher followed the outline of the cell, cutting a trench to allow for threading of the sheet piles. The prefabricated guide frames were put into place section by section, and the major work of setting piles proceeded quickly. Cranes were moved to a new location every 24 hours to avoid ice fatigue. The smoothness of the ice paid off as the piles were moved into position near the cranes. The crew said that handling the piles was like moving so much spaghetti. To deal with this flexibility, a system of special bridles was rigged so that each pile could be lifted by multi-grasped cables swung up without getting permanent kinks. The bridles were easily disengaged. We used a single external guide frame supported on ice. This drastic departure from the time-honored method of using double internal guides supported on piles simplified the work. This simplification, together with the use of equipment which could work from a man-made ice platform, created extensive cost benefits. The 80-foot sheet pile blew in the wind like a sail. Only the best riggers and operators could work under these conditions. If each pile wasn't dead plumb, the ring wouldn't close. Most of the pile driving was done by our electric vibro hammer. We used it on both the ice platform and on the land side, where the weight of the hammer was within safe operating range of the crane. Under normal conditions, the crane swings the hammer into place easily, but in this wind, it takes manpower as well. The hammer literally shakes the pile into the ground. Springs on the suspension bar keep the vibrations from reaching the crane. Amplitude and frequency of the vibrations are adjustable to the length of the pile and the type of soil. Rapid staccato impulses pass from hammer to pile, causing soil in motion, and the pile sinks effortlessly into the silt. The piles are keyed 1 or 2 inches into bedrock. For the side walls where the vibro hammer couldn't be used, we constructed a drop hammer out of 3 H-beams. Because of the freezing cold, no engines were ever turned off. Each pile was numbered and its length and location was recorded. As the pile got near the bottom, its progress was closely monitored. Complete record was kept of its driving resistance per foot penetration and its final set resistance and elevation. The uneven lines of the piles already set reflects the unevenness of the bottom. Throughout the pile driving operation, divers inspected the interlocks. A video camera was used to provide a permanent record on tape of every pile. With rising tides, ice, add freezing to the steel, could lift the piling. To avoid this, the steel was coated with calcium chloride embedded in grease. An unexpected problem could arise as quickly as a change of tide. Occasionally, ice wedged against the incomplete structure would have to be cut up and grappled out. Heavy equipment was separated by at least 100 feet, and vehicles moved at no more than 10 miles an hour. The job was on schedule. Temperature minus 10 degrees Celsius with a wind gust 35 miles an hour. Not much of a day for a visit from the Queen's representative. Besides his official interest in Canada's northern development, the Governor-General is personally interested in the history of the Northwest Passage. The engineers describe the sophisticated marine terminal that will stand here. Perhaps he thought of Franklin and his men who passed down this very strait in 1846 before they sailed on to be lost forever in the ice. The closure of each cell was an anxious time. Even a slight misalignment in the work so far would mean the difference between a smooth operation and a considerable delay. The last pile threaded was always a Y pile, which is more rigid. The main cell with a small adjoining cell. To complete the job, while heavy equipment could still be safely used on the ice, it was necessary to run a double shift of 12 hours a day, 7 days a week. Even the dogs worked in shifts. After each cell was closed, it had to be cut to the planned elevation of 15 feet above mean tide. After every half-dozen piles, we left 2 uncut to support the cut steel while waiting for the crane to remove it. The trencher was swung in to prepare for removal of the ice disc inside each cell. The disc might weigh up to 100,000 pounds. It had to be cut and lit before the earth fill was put in place. But there was one more problem to be solved. The layer of silt and stones on the bottom was firm enough to retain the piles during construction, but pressure of the earth fill could squeeze the silt outwards, forcing the piles apart. Our solution was to clean out the silt at the front of each cell and replace it with coarser fill. As the rest of the earth fill was added, the pressure at the back and sides would be balanced by the outside fill. Excellent material for the replacement of the front silt was available from the mill basin. The cells and the space between them and the shore required a considerable amount of fill. We built a narrow 60-foot bridge from the dike to the cells and brought in a conveyor to place the fill to the water level. The weathered limestone, dug from the mill basin the year before, was workable even in winter. It had low moisture content because of the dry air of the Arctic desert. The remainder of the fill was moved by truck. Ultimately, the earth fill will become permanently frozen, forming a strong structure. The sun at low tide, or a warm surface layer of seawater in summer, could soften the permanently frozen fill at the front of the dock. To prevent this melting of the fill, a 10-foot strip of insulation was applied inside the piles before the final fill was added. Two days after the work from the ice platform was completed, a thaw set in. On May 20th, we began to demobilize. The material and equipment was moved off the ice as possible. By mid-August, the ice will be completely gone, and the silt and rock debris remaining on the platform will have sunk to the bottom. For a short 6 weeks each year, huge ore ships will tie up here. The completion of the dock within 3 months is an example of how we meet the challenge of the Arctic on its terms: cold.